Alicia does cut it. Okay, so you're fine then. Just don't say anything now. Stefania, just in case. No.
We're recording.
Yeah, seems to be working. It's a bit strange, but it should be charging, hopefully.
Do you want a pointer? You want a pointer?
Yeah, anything. Also, like a stick.
We don't have a stick.
Oh, okay. Yeah.
Okay, well, yeah, we'll be back. Yeah, we should have a sticky, but people take it.
So you are sharing screen.
Can you check?
Yeah,
I think
think
she's
so.
doing that correctly.
Yeah, okay, you're sharing this screen, not that screen, just like you are fine with that.
What I'm sharing? Sorry?
You're sharing this screen, not that screen.
Oh, wait. Then let me redo. Thought that I was sharing the correct one. Let's see. You're right.
Yeah.
Okay, now it should work.
Let's do this one. Stop sharing.
Let
Let me just make for that one. You want the full screen for this?
Yeah, but first you should share, I think.
Okay. So now can I pull any information?
No.
Okay.
No, you have to. Yeah.
I see.
But before it should work, I think.
Okay.
Oh, so that's
this one. I think desktop 2 is that screen, right?
Are you sure?
This is a document, but this is the screen. Either way is fine. Good. Okay, so you can play that one now.
Yeah, maybe if you could check just to make sure. Because I thought that I was sharing that one there.
I can check.
Okay.
Yeah, but I think this time it's sure.
Okay.
Okay, I think we can get started. Well, it's a pleasure today to introduce Stefania Gori. Stefania got her PhD in Munich in 2010. Then she did postdocs at University of Chicago and Perimeter before becoming junior faculty at Cincinnati. And after Cincinnati, she ended up at UC Santa Cruz, where she's professor today. And she will tell us, and today she's going to tell us about new ALP signatures at high intensity experiments. Okay, thanks. And yeah, thanks for inviting. It's a pleasure to be here again. Apparently I was here in 2017. I didn't remember when it was. So yeah, for today, I'm gonna present some work that I've done together with my collaborators on axion-like particles and new probes of these axion-like particles at high intensity experiments. So since this is gonna be a talk about axion-like particles, I have a couple of slides of introduction that, you know, the usual slides about Y axions. I'm sure that we have heard this too many times. So we are interested in axions and axion-like particles in the context of the strong CP problem. And this is a problem of small numbers, if you want. Namely, if you think about QCD, we know that we can write down operators that are breaking CP. But at the same time, we know that we have stringent bounds on CP violation coming from neutron electric dipole moments, telling us that these operators should have a coefficient that is very much suppressed. And one class of solutions of this strong CP problem is coming from having this Peche-Quinn approximate symmetry that is spontaneously broken. It leads to the appearance of this new particle, the axion, that has a potential that is minimized at its theta bar equal to 0. The interesting property, the additional interesting property of axion is that it can be a good dark matter candidate, and this has motivated a lot of both theory and experimental effort in trying to understand what are the properties of these axions and how to discover them.
But then if you look at the status, the present status of testing axions, here is where we are. So this is a plot that I've taken from the Snowmass white paper on axions. And we see the several colored regions are the regions that are already probed. In this plane where we see on the x-axis the mass of the axion, and on the y-axis it's coupling to photons. We know that we have this relation, so that the mass of the axion is inversely proportional to the decay constant. This is what we see here for the most famous axion models, so this KS, VZ, and the FSZ. And what you see is that at the moment, there is a large regional parameter space that is unexplored of these models. There is only these ADMX experiments and a few more that are, having access to this line. But what is interesting is that there are a lot of proposed experiments. Some of them are approved that will be probing a much larger regional parameter space for these axions. And you can see that in the future, we expect to have, a sizable part of this line that will be probed. Okay. Also notice that for this plot, if you look at the scale, we are talking about sub-EV new physics. Okay, this is where this type of models work. And then the question is, okay, can we go to higher masses? Are there models for addressing the strong CP problem with heavier axions? And there have been a lot of activities both in the past and also quite a lot in the recent years, trying to write down models in which axions, those that are addressing the strong CP problem, are heavier. And these models are less minimal in the sense that we need to add additional interactions and additional axions. Usually the way it is done is to introduce additional gauge group where our strong SU3 is part of this bigger group. In particular, for example, in this paper here, what we're doing is to consider some product of SU3 broken to the diagonal SU3, and the diagonal SU3 is our own SU3, and each SU3 has its corresponding axions. These are more strongly coupled SU3 that are leading to heavier axions. Okay, and this I'm bringing this as an example to say that there are models that lead to axions that are much heavier. If you read here the numbers, this benchmark here have axions that are even in the MeV or GV range. Okay,
and then the dashed line. What is that? I think the dashed line was. I think that was when the axion decays.
Yeah, I think
so it can't become dark matter.
Correct. Yeah, the solid is dark matter, and then afterwards it's not dark matter anymore. And then actually here, I mean, we can go more into the details of this model, but there are two benchmarks here in blue and in red, depending on how many SU3s you have. I think this in blue has 3 SU3, and this in red has 2 SU3s. But yeah, the specific relation between MA and FA depends really a lot on the model, and you can build really models in all the regions that you like. Is also no, you have a strong dependence on the scale where this is broken, and that's why you see these sort of kinks in the lines, and this is exactly because you have a breaking of this 2 SU3 at I think they fix it at 10 to the 14 GV. So that this to say that there is a lot of freedom. Yeah. Correct. Yeah. That's right. Yeah.
Are there matter associated with the others?
In this specific model, not. There are other models in which there are also matter fields. Yeah.
But you said they get strong earlier? Higher scale?
That's correct. Yeah, that's let me see. I think that there is only so our matter fields that are charged under everybody, I think, if I remember correctly, but no additional matter field. Yeah.
So our counterparty are charged under ISO-3 1 and ISO-3 2.
Right.
It was broken at higher scale, so diagonal. We identify diagonal. There's no actual error.
Right. But yeah, the key is that our matter is charged under everybody. And then you have this breaking at high scale. Yeah.
They have multiple axions.
Correct.
So mix those back.
Correct. Yeah, that's why you see several lines here, and each line corresponds to one axion. Yeah.
When you say the solid corresponds to dark matter,
yeah,
do you mean, do they have a production mechanism, or that's just the long?
I think it's misalignment, and then that works in some specific region of parameter space only.
But I think it's just long-lived.
Okay, yeah. They're just saying it's long.
Yeah.
It's just when it's dashed, if I remember, it means that it can't be done.
Correct.
Yeah, okay. Like if you wanted misalignment to work, it's part of the parameter space, you might need to do funny things.
Yeah. True. Yeah. All right. So this
question.
Does
that come from light?
This yeah, apparently. Yeah.
How does light?
Oh, that's a good question. Honestly, I didn't go through all the experimental constraints on this specific model, I have to say. Yeah. Maybe we should look offline about this. Yeah, this is more, to give you a proof of principle that there are these models with the heavier axions and how possibly they can work. Then details, they are super much model dependent as well. Yeah. All right. And then, to complete this couple of slides of motivations, we know that there are also additional motivations for considering heavier axions. And in general, from my perspective, it's interesting to see the physics associated to basically non-Goldstone bosons that are light and that are coming from spontaneously broken global symmetries. And a lot of times, there are many models that lead to these particles, and a lot of times the phenomenology is very similar. So I think it's interesting to see what type of phenomenology arises from this type of particles, and then we can interpret that in terms of concrete models. And then, as it is listed here, you can interpret that in terms of, even models with for extended supersymmetry, like the NMSSM, where you add your approximate Chipman symmetry, or models that address the hierarchy problem-like relaxation models. There have been studies in which these axion-like particles address some of the anomalies. We can believe or not in these anomalies, like G-2. But this to say that it's pretty generic to have these axion-like particles in the sub-GeV mass range. And then the question is, indeed, how they communicate with us. And then we write the EFT of these axions. And so we want to write down a Lagrangian that has an approximate shift symmetry. We can, for a CP odd particle, we can stop at dimension 5. And this is all that we can write down. So we have these couplings with gauge bosons. These are gauge bosons, so the standard model. And then all these derivative couplings with fermions. In principle, we can write down also this coupling here with the Higgs of the standard model, but actually it's relatively easy to see that this is a redundant operator. So we can do a phase shift in the several fields of the standard model, so the fermions and the Higgs boson. And then for specific phase shifts, you can show that you can kill this operator and just shift the operator, the coupling with fermions. Okay. So basically, from the phenomenological point of view, we can restrict ourselves to this Lagrangian here, and then see how to test these couplings.
And these are the authors that also found a mistake in the original paper.
Sorry?
The authors, these authors, Bauer and ALP,
yeah,
paper that found a mistake.
Yeah, in the paper by Randall. Yeah, so
it's the same paper.
So they wrote many papers. I don't think this is, I think this was a 2021 paper that you have in mind. They have a series of papers, but the one that you have in mind is a paper where they point out that there was an extra contribution to decays like K2 pi A that was not discussed before in the literature. Yeah. Yeah, so in terms of couplings, so phenomenologically, this coupling here with photons that comes from these two couplings here after electroweak symmetry breaking is the one that has been the most studied. Then, of course, this coupling with gluons is very important because, you know, if we are interested to solve this, solving the strong CP problem, then this is the coupling that we should be interested to. And then there is all a large set of coupling with fermions that has been not incredibly explored compared to other couplings. And that will show that there are some interesting aspects of this coupling with fermions in this the second part of this seminar. And overall, there are a lot of experiments that we can put together to constrain these couplings. So we can go to high energy. We can use low energy flavor experiments, in particular for flavor violation, fixed target experiment, as well as meson factories. And then for this, so I'm collecting a few references, but there are many, many more. And for this specific seminar, I will show you a couple of things that I'm quite excited about. And in terms of experiments, we'll focus on these fixed target and meson factories, and I will explain why. And in particular, I find myself quite excited about these two experiments. On one side, DarkQuest, on the other side, Pioneer, and we'll learn quite a bit about these two. And of course, we'll show the complementarity of these experiments with other experiments and how they work. Now, the reason I'm excited about these two is that from the point of view of meson factories, we have several meson factories that are running now in the future. And we know that we'll have a much larger statistics of mesons in the coming years. So here I've done a table that is summarizing the status of pion factories, kaon factories, and B factories. So for pion factories, we'll learn quite a bit about Pioneer, and this is an experiment that has been proposed for PSI in Switzerland, with the idea of collecting something like at least an order of magnitude or so more pions compared to previous generation of pion experiments. Then we have kaon experiments both at CERN and at JPark. Again, if you look at the numbers, we are planning to collect at least 1 or 2 orders of magnitude more kaons. And then there are also these proposals for HIKE at CERN, so next generation of kaon experiments, and COTO2. Actually, there were talks in the ICFA meeting today. I didn't check the slides yet, but let's see if there are news on this HIKE experiment. And here you see that the goal will be to collect even 1 order of magnitude more kaons if compared to present experiments. And then for B factories, as we know, we have LHCb and BEL2, and again, this is the status of data. So far, LHCb collected a little bit more than 10 inverse of random data. The plan is to have more than 20 times more statistics. And even for BEL2, so far, there is not incredibly much data. Well, relatively speaking, so we are talking about an amount of data that is comparable to what BEL collected. And in the future, we'll have something like 50 times more, okay? So a lot more data will be collected, and just thinking about data, I think this makes this field very interesting. And in the context of pion factories, there is this Pioneer experiment, a cartoon is given here. So the way it works is that we have a pion beam that is then stopped in this active target that you see here. And once it is stopped, we want to measure very rare decays of these pions through a detector that is all around this active target. And so this is, there have been the proposal for several stages of this experiment. And as far as I know, only the first stage has been approved by PSI, modulo fundings. And then, so they have a lot of standard model measurements that they want to do at this experiment. And in particular, they want to improve in the measurement of these standard model decays. So these rare decays of a pion going to a positive neutrino, as well as this beta decay of the pion. And then what we are pushing for are searches for new light particles that are produced from pion decays. Okay. So this is one experiment that we'll use for testing our ALPs. And the other experiment that I'm quite excited about is DarkQuest. And this is a future experiment that is proposed for Fermilab. So you see here, this is the accelerator complex of Fermilab. And there is this exit here, or the accelerator complex, that is taking part of the main injector, the 120 GeV proton beam. And this sent to this experiment here. So this is actually an existing experiment that is called SpinQuest. And you see, looking at this cartoon, you can see that this is a beam dump experiment. So this is your dump. These are 5 meters of iron. And then afterwards, so there is a magnet here that is called K-mag. And then here there are several stations of a spectrometer. So what SpinQuest can do is to identify super well muons. Muons that could be eventually produced from dark sector particles like axions that are produced, they go through this dump and then they decay afterwards. Okay. And what is DarkQuest? So this is an experiment that we proposed a few years ago. And so this is an upgrade of SpinQuest that consists in adding additional part of the detector. And in particular, some calorimetry such that we will be able to identify not only muons, but all, charged particles, photons, and so on. And so the goal is to have an experiment that is able to identify any visible signature of particles that are sort of a little bit long-lived to pass through this dump, okay, and then decay afterwards. And so we might have heard a lot of about beam dump experiments, but this is quite unique because for several aspects. Probably most importantly is that this dump is pretty small compared to previous beam dump experiments. And we can compare just dimensions. So the dump here is 5 meters. If you take other proton beam dump experiments, you see that we have something where the dump is much, much larger. And this tells us that we'll have access to lifetimes that are much shorter for these dark sector particles. And then here you can see other numbers that are, defining this experiment. Namely, the proton energy is quite high compared to other experiments like LSMD, as well as, the amount of data that hopefully we'll be able to collect is quite large. Okay.
But so if the energy is higher, then also you get gamma.
Yes. Mm-hmm.
Is it against what you said?
Yes, it's still consistent with that the dump is relatively small, even introducing gamma factors. Yeah. Oh, well, for LSND, yeah, for LSND, I agree. I was thinking more about like charm type of experiment. Yes. No, for that, I agree. Yeah, that's right.
What was the SpinQuest's main target? Can I go back one slide?
Main target mainly, namely physics reason to exist, or yeah. So the 1 second. Okay, here. So originally, so this is a nuclear physics experiment. So the target that they have is a polarized target, and they want to do measurements of Drellian dimuon production to extract proton properties like PDFs and spin and so on. So this is simply in the context of nuclear physics. Then nowadays we have a sort of a working group inside SpinQuest for dark sector searches, because you can do searches for particles decaying to muons, and this you can do already with that experiment. For nuclear physicists, they care a lot about the target. For us, we don't care of the target, but we care of the dump. But then, it's just a matter of recording muons. We know the origin of these muons, and then we can do the analysis that we want. Yeah.
So basically, they are trying to do EPS and polarized.
Correct. Yeah, that's right. Mm-hmm.
Polarized.
Yeah.
And these ALPs, they can still be the dark matter.
No, this decay. Yeah. No, none of the ALPs we'll discuss are dark matter. Everything decays for us. Yeah.
So it's just more of a heavy axion. So strong.
Correct. Yeah, it can be still invisible, but I don't think any of the model that we discuss can be dark matter candidate. Yeah. All right. So. Yeah, and then an interesting aspect also of this experiment, or in general proton fixed target experiments, is that they produce tons of mesons. So before I was arguing, that there are these meson factories that will be producing a lot of mesons, but actually these proton fixed target experiments produce even much more mesons. So if you look at numbers for light mesons, we are talking about many orders of magnitude above the statistics that we'll be able to collect at like pioneers or kaon factories. Okay. And also, there is a little bit of a piece of news that we got finally funded for this experiment for DarkQuest from NSF. And then this is hopefully our time scale, where now, I mean, modulo the running of the terminal accelerator complex, SpinQuest will collect the data, and then afterwards we can upgrade our experiment and then do this DarkQuest experiment afterwards. It's not much, yeah, because it's just an upgrade of this. It's around $1 million. Yeah, I mean, this is just for construction. Then there is operation and people working, salaries, and so on. But for the experiment itself, is around $1 million. Yeah. All right. So then next, we want to understand how to produce axion-like particles at all these experiments, and there are different ways of producing, either directly, what I would say, direct production from beam collisions, so all these type of diagrams here, or also from meson decays, either neutral currents, so flavor-violating processes like this, K2πa, or charge currents where we don't change the flavor of the quark, and this is one example. Okay. Then, of course, you can have also other decays, like from the Z boson, from the Higgs boson, and we see that there is a lot of complementarity between all these different production modes. And what I will highlight is actually an interesting complementarity between neutral currents and charged currents. So actually, in the literature, there have been much more studies for these neutral currents here. These type of decays can arise in many different models for ALPs. Now you can have ALPs that are mixed with the neutral pions of the standard model, and then you get these decays. If you couple the ALPs to W boson or to tops, to leptons, these are pretty much generic decays. For charge currents, you can achieve them if you have models in which you mix the ALP with your pion, as well as models in which axions communicate with the leptons of the standard model. And what I find quite surprising is that several calculations for these decays have not been performed in the literature. And there are also, as I will point out throughout this seminar, several experimental searches are not yet done. So I think it's very interesting to try to cover all possible holes. And whenever the experimental searches are not done, our job, if you want, is to reinterpret other searches or measurements, in particular of standard model processes. And what I will show you is that we can actually take standard model measurements like the pion decay to a positive neutrino or this beta decay to set constraints on this axion production from pion decays. Okay, so these are purely standard model measurements. Okay. So having said all of this, let me give you a couple of examples of models and how to constrain them. So this will be the two classes of models that I will investigate with you. On one side, we will study axions that are mixed with the pions of the standard model. And this comes generically in axion models, because if you couple the axion to light quarks or to gluons, then automatically you get this mixing. And then the second part will be dedicated to axions that are coupled to leptons. So let's start with the first one. And so, as I said, if you have this coupling with gluons as coming from, addressing the strong CP problem, then you get this mixing. And then what do you do with it? This mixing will lead to this decay mode of the pion to a positive neutrino and an ALP. And we can compute this decay. So the amplitude will have different type of contributions, both from this charge current and neutral currents. And actually, the leading factor, as we'll argue, is this term here that is coming from the axion mixed with the pion. And computing the amplitude, we will have dependence on two form factors. Actually, only one of these form factors is important because this F0 will lead to a contribution that is suppressed by the mass of the electron over the mass of the pion square. And so knowing this form factor, this is approximately equal to 1 if your Q square, the momentum exchange is not that big, then you can compute all your branch ratio, including you know, the differential branch ratio and compare to experiments. And what is interesting to notice here is that this decay mode here is not suppressed, so you don't have helicity suppression nor phase space suppression, contrary to the corresponding standard model decays. So this, even if the mixing angle is small, you expect the branch ratio possibly being sizable. Okay. And you might wonder about other. Pi 0. You don't have helicity, but you have phase space suppression. True. Yeah. Just a standard model either has helicity suppression or phase space, depending on what you take. Yeah, definitely.
So lack of phase space suppression, that's because the axion is much tighter than.
Yeah, it can have any mass. Of course, if you take the ALP being close to pi plus, then you have a phase space suppression, but generically you don't have this.
Did you also say on this slide you don't want it to be too light?
Yeah, so you don't want to have it. So this approximation here breaks down if you go to ALPs that are super light. But you know, if you consider like MeV, 10 MeV and above, this is a good approximation. Yeah.
Okay. So you're thinking like MeV to 100.
Yeah, something like that. Yeah, those couple of orders of magnitude in mass where this holds. Yeah. Yeah, so you might wonder about additional contributions, because here, in principle, you can sum over all standard model mesons with right quantum numbers. But actually, this will give you additional contributions that are, however, suppressed by heavy meson masses. So they are quite small if compared to the contribution that we discussed at the previous slide. If you have this ALP pion mixing, you might think about also computing things like K to pi A. But actually, this type of decays are much more model dependent compared to pion decays. Reason being that you can have additional contributions from SD penguins, so diagrams like this. And these generically, even though they are one loop contributions, they are generically larger, okay, because of this M-top dependence here. So in general, even if you have some contribution from the mixing, you expect that theories will give you much larger contributions through diagrams like this. Okay. And once they are produced, then the question is, of course, how these axions will decay. And so if we have the mixing with the pi 0, the standard model, in general, you can expect that they can decay to photons because they will inherit the coupling with photons from the pi 0. Of course, it's not a one-to-one correspondence because you can have some UV contribution to this photon coupling on top of this mixing contribution. And then, of course, if this coupling to photons is small, you can expect that they are simply invisible to our detectors. So in terms of signatures, you can have either these 2 photons plus positron missing energy signature, or just a positron plus missing energy. And interestingly enough, what I want to point out is that this search here, a dedicated search for a resonance decaying to photons from pion decays has not been done. And so the bounds are coming just from standard model measurement recast. Okay, so it will be interesting to see indeed if this can be done at Pioneer. And so let's see what recasting standard model measurements, what can give us.
But this mixing is a 3-parameter.
Right.
And that's because you're assuming that there's some other mechanism that answers the mass, because in QCD, right, they're fixed, right? Right.
Yes.
So this 3-parameter is related to the mechanism that makes the axion heavy.
You can, yes. Yeah, we'll see in, no, we won't. So even the papers that I was mentioning before, you can relate the two. So once that you have this Coulomb coupling, and then or your QCD sector, then you can relate the mixing to the mass and everything. Yeah. So for our analysis, we consider it as a pre-parameter, but I agree with you that then you can match to the several theories and yeah.
So you consider it as a free parameter.
But following this question, I still do not follow. If mixing of axion with pion could be arbitrary, what was this say heavy meson does not look that it makes sense, right? Why heavy meson would be separate?
So the kaon decays you're referring to, or?
No. If it's about mixing of axion with pion, and you do not know the nature of this mixing, then what in your first line, it looks like a contribution to this mixing from the heavy meson, right? Maybe I got it wrong. But why this heavy meson contribution would be special if you do not know mixing with a pion anyway? Or because it's mixing with a charged pion, or what is the point? It is a mixing, effectively it's a mixing not with pion, right?
Oh, you are referring to this part here, that you can have additional mixing with heavier mesons that are contributing since you don't know. I agree. So
I see. So it's not mixing with a pion essentially, right? Because it is.
Yeah, you have mixing with the mesons that you can mix with.
With a meson, yeah. I'm sorry. Yeah, I thought that it is like a mixing with the neutral pion. So that's why I asked.
Yeah. No, I completely agree. Yes. Yeah.
I see. Okay, sorry. Thank you.
You had some other question? Or?
No,
Okay. Okay.
In terms of the decays, if you think about axions heavier than an MEV, you make couples to leptons, kind of decay to like electron proton.
Yeah, we will see it later. Yes, you can.
But the dominant decay is still.
It depends on the model. Yeah. For this model, if you focus on this effect here, that the main effect that it is describing your phenomenology is coming from the mixing, then you expect the photon to be the main decay mode. You cannot decay to anything else. Correct. Yeah. K2 pi gamma gamma. Yes. True. Absolutely. Yeah. Once that you go to kaon decays, then there are photon signatures. I agree. We were for our paper, we're not particularly interested to kaons because of this reasoning here, that then it becomes really a matter of, considering. Sure. Yeah. Is I agree. Yeah. So in terms of standard model measurements that we can use, is actually pretty cute because so we can take the pion. So this was a old pion experiment measuring this decay mode here in the standard model. And what they did was to measure very precisely the positron spectrum, and then luckily enough they give us the residuals of their data as a function of the energy of these positrons that are collected here in the detector. So just using residuals, we can draw our differential distribution coming from this decay mode, and then compare with data and then extract a bound. Of course, these distributions will depend on the axion mass. Here there are two examples for axions of 40 or 80 MeV, just to give an idea. And this is in the case in which the axion is invisible, so it just escapes the detector without any further energy deposit. And then you can do the exercise in which, for which the ALP decays to photons, and then some of these photons enter in the geometric acceptance of the detector. And this, of course, will change the distribution. And then you can compare with data and extract a bound.
If I just naively treat the axion I0.
Yes.
And I will compare this with an A16. There you are sort of at the 10 lines.
Yeah, not clear because so the we are constraining also branch ratios at the level of 10 to minus 9 here. So it's not clear how it would play. Probably they're comparable, I would say, but I didn't put precise numbers, just assuming mixing. But yeah, it's an exercise one could do, just assuming mixing and then compare kaons and pions. True. It just it's just that I would find it sort of hard to find a theory that then matches to this just mixing scenario sort of. But I agree with you. Yeah.
But this mixing implies that you know, it's in certain way it's not an axionic type, right? Because if it's going to say kind of limit where this x as an axion, then it should be invariant under the shift of way, right? And those mixing are not invariant, right? So in this way, no, it only in kind of symbolic sense is axionic.
Yeah, true. Yeah.
I see. Okay. Yeah. So I mean, okay. So then any kind of scalar particle, you know, with the proper quantum numbers would be okay, right? So to identify it as an axionic part would imply certain type of, I don't know, restriction in chiral limit or whatever, and this type of mixing, I mean, probably breaks it. It looks like.
True, but I mean, if you think about right, I mean, if you start like just the decoupling of an axion with gluons, it will give kinetic mixing between the axion and the pion, right?
Right. Yeah.
Right.
Okay.
Yeah.
Okay. No, like I just trying to emphasize that it's look like much more generic than axionic, right? It could be anything.
Yeah.
No, in this analysis, right? Yeah. Okay. So.
Yeah.
Okay.
Yeah. You have a question?
Yeah. Why are the invisible and soft? Like, why do the curves look so different? Kind of that would change the curve.
Yeah. So for let's see, for this is true when you go to light masses, where in general how it works. You expect because I mean the detector is only on one side, so it can be that you adjust the photons. You don't get the photons in geometric acceptance because basically you have the positron goes in the opposite side compared to two photons. So the two photons are not in geometric acceptance. If it is heavier instead, you see this is for the orange curve. If it is heavier, then you expect typically also photons to be in geometric acceptance, and then these change your distribution.
Okay.
Yeah.
You're just more likely.
Correct. That's right. And and then for this experiment is also, you know, you don't distinguish between photons and positrons really. So what you can do is just add the energy deposited and then compare with data. Then with Pioneer, it will be much better because then you can distinguish and then you can say if it is, you know, possible photons coming from axions or these positrons. So yeah. So this is one of the standard model measurements that we can reuse for these axions. And then the other standard model measurements is the measurement for this beta decay. And so this was done at pi beta. That was an experiment in the 90s. And this is a cartoon of the experiment. Again, this was a pion decaying at rest experiment, measuring photons coming from the pi zero. But then, of course, since pi zero and pi plus have a similar mass, then these photons are basically back to back. And then indeed, so these are data from pi beta, and you see that this is the opening angle between the two photons, and this is peak towards very large angles, as we expect. And this will not be the case if we have an axion that is lighter. Of course, going to lighter and lighter axions, we will go to lower and lower angles. And here it's more problematic to reinterpret this standard model analysis because they don't give us residuals. And furthermore, we have data only for opening angle up to 160 degrees, so nothing below. So if we have a lighter axions, we don't really get any constraint because of that. And so what we do was, we are quite conservative, and we say that the additional contribution to the rate is not bigger than the experimental uncertainty on the standard model measurement. And putting everything together, these are the type of bounds we get on this mixing angle. So this was the pi nu, the decay to a positive neutrino, and this is the decay to a pi zero positive neutrino. And we see that the mixing angles up to something like 10 to the minus 3 could be probed. And this is, yeah, the 10 to the minus 9 branch ratio that I was mentioning before to answer Maxime. And it will be interesting to see, especially for this decay to photons, what Pioneer can do, and especially at lower masses, because here we don't have really information from the pi beta experiment. So we expect that we can cover much more regional parameter space here at lower masses. And so it will be interesting to see. Okay.
I like their extrapolation. 24.
So it won't be this the coming month, but hopefully the month afterwards.
Pretty sure it's going to be in January.
No, I'm not sure. I'm hoping. Okay, very good. Then, you know, you might wonder about how to compare to other experiments, indeed, but then it becomes more a model-dependent question. So what we have done to compare a little bit to other experiments is to assume that so the photon-induced coupling of the ALPs or the ALP is only coming from this mixing. So this correlates basically our production mode and the decay mode. And if you do so, then you can compare to other experiments like LEP or BEL2, where you have the production of the ALP with a photon, getting several photon signatures, as well as all the new fixed target experiments where these are the several production modes of the ALP that couple multiple photons. And so the bounds that you get, the bounds that you get are these type of bounds, where in blue are the regions that we were already discussing. And then you see that, so below this yellowish line is the regional parameter space probed by DarkQuest, below here. Here you have BEL2 with one photon type of bound. Here you see LEP, and this is an electron fixed target experiment, and this is a proton fixed target. But so the summary here is that if you are in this regime, then you can probe basically the entire parameter space below the pion mass. Of course, I mean, if the mixing angle is super tiny, at a certain point, the beam dump are not anymore constraining, but you see that you can get to very small mixing angles. Okay. Oh, did we talk about this a second point, maybe? Yeah. Yeah. True. True, but true. I thought that, yeah, I thought at a certain point I put numbers that it was not competitive to this other, but it's true. Yeah, this is something that, yeah, that also can be used to constrain parameter space here. Yeah.
The time actually curves back at lower.
Yeah, this is what I was saying, that at a certain point, you cannot go.
And this is something very strong. Right? You basically rescale actually on the concept at high constraint.
Correct.
So
Correct.
Very low FA regime.
Right. I agree. I completely agree. Yeah. Unfortunately, we show a plot. I mean, this type of experiment. So for big dumps, the FA that you probe are relatively high. I mean, TV scale or even above. For these pion experiments, is very, very low. Yeah, that's true. That's the capability that they have. Yeah. Yeah, so I'm running a bit out of time, so maybe we skip this. So here I wanted to point out that there is a lot of experimental work in understanding for DarkQuest this reach that we show here, and in particular on backgrounds. So this, yeah, I'm part of the collaboration since we proposed this experiment, and now we are studying quite in details the background to photonic signatures. But maybe I can skip that in the interest of time. And another thing I wanted to point out is that, so these are bounds that are very phenomenological with the goal of setting a bound on this mixing angle. And then you can match the theories, or you can match two EFTs, and in principle, two models that have a reason to exist. In particular, there are no studies in which these axion-like particles are mediated between us and the dark matter. Here I'm reporting a couple of examples recently. So we wrote a paper, and then there is this other paper here. And I'm taking a plot from this paper, where basically they were coupling these axion-like particles to gluons as well as to a dark matter candidate, and then studying what models can work in such a way that this sky particle is a good dark matter candidate, both in freeze-in and freeze-out type of scenarios. And for freeze-out, they show a plot like this. So this is the mass of the ALP, and this is the decay constant, this separate here. There are several regimes depending on the mass ratio between dark matter and the axion. So if the axion is lighter than dark matter, then this is the main freeze-out mechanism. It can be close to threshold, or the axion can be quite heavier. And then you get these curves here depending on the dark matter mass. Okay. And then to place that in the context, actually, if you are below the pion mass for the ALP, you can cover all these models here, either from pion decays or proton beam dumps. But then you see that indeed the FA that we are considering is very low. Okay, and this is the FA that you need if you want to have this thermal freeze-out mechanism for that matter. Okay. All right. And so this was for the first part, and then the second part I wanted to discuss with you are axions that are coupled to leptons. And here,
I'm sorry, but returning back to this mix, if you rotate, do axial rotation of chi, you will go to the second term, right? It's they are kind of in certain way it implies certain frame, some calibration, right? Because you can move from one component to another by the definition of the field.
True. I completely agree. Yes. Here, yeah, is the way they do it. I agree. Yeah, the way they do it is to fix this coupling with dark matter, and then you have the same decay constant for both. And but I agree that one can reshuffle things around and.
Okay, thank you.
True. Yeah. No, I agree, but you can reshuffle things a bit around, right? Depending on how you define the fields. Yeah. All right. So here basically the starting point is an EFT like this, where you write down possible couplings to leptons. Here I'm putting electrons, but it can be muons and so on. And what is interesting is that something that we notice, because ultimately we wanted to compute the processes like this. And we noticed that, there are some claims in the literature that can be a bit misleading, like that this G-bar coupling is unphysical. So basically here, what you can see is that, so you can, redefine fields, and what you can see is that there are only two of these couplings that enter this type of decay. And the other one is the anomaly coupling. So once that you do calculations like this, you see that indeed there is only two linear combinations that are physical, and you see that actually there is only one contribution that is not helicity suppressed, and this contribution is a contribution that goes to zero once that you consider SU2, our SU2. So SU2 will of course put some relation between these three couplings. And in the limit of SU2, this combination will go to zero, so you have helicity suppression. But if you have SU2 violation, and this is a term that is there in this rate, and this, of course, will lead to much larger pion decays. Okay. And of course, the question is how to get this SU2 violation, and this can be generated by models. You can even generate it by running FS below the electroweak scale, so QED running. We are studying this, but it's quite suppressed actually. But then you can have models, as we see, like with the sterile neutrinos or vector-like leptons that do generate this SU2 violation. And a very simple example is an example like that, where you have a sterile neutrino that is charged under the PQ symmetry. It has a Dirac partner, this MC, and then once that you can redefine this field, and then after electrosymmetry breaking, the sterile neutrino will mix with the neutrino of the standard model, and then you regenerate couplings like this for the ALP that are only with the neutrinos of the standard model, but not a corresponding coupling with charged leptons. So effectively, you have this SU2 violation that depends on this mixing angle. But then putting numbers, so depending on the specific model for the sterile neutrinos, these mixing angles can be pretty large still, and they can generate couplings that are accessible as we see for experiments. Okay, so this is a sort of a proof of principle of models that can lead to this SU2 violating EFT for ALPs that we are discussing here. And another way of seeing this type of physics is that we can go to a basis in which the ALP coupled to the derivative of a current. And you see that we have the standard vectors that have been super much studied in the literature, anomaly terms, and then this weak, what I would call a weak vertex between an ALP, a W boson, charged lepton, and a neutrino. And this is, again, as we can see here, this goes to zero in the SU2 limit. So you need to have this SU2 breaking effects to make this a relevant part of your Lagrangian. And so once you have that, then you can compute all the several processes. And in particular, this charged pion decay to an ALP will be now enhanced in these weak violating models. And the enhancement factor is this m pi over me square. So we get much larger branch ratios in the context of these weak violating models. And this is true not only for pion decays, but also, any of these charged current decays will have this enhancement factor. And then the question again is what type of data we can use to constrain these models. And so there was this syndrome experiment in the 80s that was looking for this signature. That is exactly the signature that is coming from this scenario. And this is a plot taken from this syndrome paper here. They constrain the branch ratio as a function of the mass of this new particle and its lifetime. And you see that we can constrain branch ratios at the level of 10 to the minus 9, 10, even 11. Yeah, yeah. Different goals and different times. All right. And then, yeah, you can use this to set a constraint on this coupling, both in the weak preserving and weak violating models. Of course, in the weak violating models, you have access to smaller couplings because of this enhancement. And then the question again, what we can do at Pioneer, here is a line for if we get a bound on the branch ratio at the level of 10 to the minus 11 to see how much more regional parameter space we could probe. But this is, something that we are currently investigating to see if indeed the 10 to the minus 11 is something that is achievable or not. You can compare, now we have a coupling with electrons, so you can compare to a plethora of additional experiments like BABAR, as well as electron fixed target or beam dump experiments. And here you can see the complementarity. Okay. There is not only pion decays, but there are a lot of additional charged current decays like PEM decays. Same story. Again, there is no search as far as I know. So what we have been doing is to take this old experiment at Brookhaven that was looking for a kaon decaying to 3 electron positrons and the neutrino in some specific kinematic region. And then reinterpreting this standard model measurement again in terms of this production mode for the ALP, and then this red region is the region that we are able to probe. And again, to guide the eye, we are putting this line at 10 to the minus 12 for possibly what perhaps an 862 could be achieving having a targeted analysis.
Do you require axion decay action or axion decay?
No, we are not requiring anything in the sense that we are computing the lifetime of the ALP I mean, it will decay to electrons, and if you are here, it is prompt. So you have 3 electron signature here, and they end up in signal regions of this measurement.
And what was the source of the weak violation? Did you have a model?
Yeah, so one example is this. So this is something that we are currently studying more in detail, but this is one example where you have stereo neutrino mixing, and then you only generate this coupling to neutrinos. But then, yeah, right here, you can do the same, you can play the same game with vector-like leptons that then mix with the electron of the standard model, and then they give you only this combination here. And this is a
dimension 5 operator previously that has this weak violation, but the scale of that of where the new physics would appear, but that's where you integrate back in the right-handed shrink. Is that what happened?
Yeah, so
it sounds like you integrate after right-handed neutrino get this weak violation.
Correct, yes.
And then you had a dimension 5 operator. Oh, there's one there, yeah, it's that one there. Well, yeah. There's one on the slide before. Yeah. And you had it suppressed by N. Forward, right?
I'm a little bit, what are you referring to?
Keep going. It's the one with the there.
Okay.
There the other dimension. Yes.
This one, yeah. This is exactly the Lagrangian we were seeing before, yes. And this
scale is pretty high. Is that right?
Is not that much high. Yeah.
Sorry.
Correct. Correct. Yeah.
That was my question. Sorry.
Yeah. Yeah. I mean, for the phenomenology that we are testing, we see, but this FA is at 10-100 GeV at most. Yeah, it's not that high. Yeah. And also, yeah, these models with stereo neutrinos, we are considering this type of masses that are also pretty light. Yeah. Yeah.
Because if FA, yeah, I wanted to see what happens if FA is really.
No, then exactly. Yeah, that's right. Yeah. And yeah, the last thing I wanted to mention is also LHC could do new searches probing this scenario, because you could have the W decay to a charged lepton and neutrino and an ALP, and this is something again that has not been done yet. So it would be interesting to see what type of constraints LHC could be setting on this scenario. And again, to have an idea of what we could possibly do, so here, this yellow region here is the region that we are probing, just considering the uncertainty in the measurement of the width of the W. That is, of course, super conservative. So we say that this branch ratio is not bigger than the uncertainty on the width, and this is what we get. If we are able to probe branch ratios as small as 10 to the minus 5, we would be probing everything above this line here in yellow. And we pick 10 to the minus 5 because actually, according to PDG, there are W decays to 3 pions that are measured at the level of 10 to the minus 5. So it doesn't seem to be completely crazy, but again, this is something that experimentalists should be studying to see how low one can go in this branch ratio. And so this is simply from, considering these charged current induced decays. And but then since we have these new decays that are coming in these SU2 violating models, so then we should redo exercises also for other experiments like proton beam dumps. The reason being that, if you take a proton beam dump like CHARM, there have been a lot of studies for ALPs that are produced from meson decays, like K2 pi A, no? But then what was missing are these decays of this type here, no? These charged current decays. And so there will be new production modes of the ALP, even at proton beam dump experiments. And then the idea is that you produce this ALP, then that is long-lived, and then the case 2E plus E minus that you see in your detectors. And so we have done the exercise, and actually for CHARM, we are just improving a little bit the reach, but not that much. as you can see here.
Is in the weak violating case or weak?
Yeah, this is weak violating. Otherwise, this
So
effect
you-
is not there.
Yeah.
Yeah.
You're with weak violating, I'm only modifying the rate by a little bit.
Correct. Correct. Yeah. Yeah. And then the question is also what one could do at DarkQuest. We have not done yet the exercise. Here also there are other interesting aspects, namely, and we can talk offline if people are interested, that since the dump of DarkQuest is much smaller, one could consider also the production of the ALP towards the end of the dump from kaon decays. And this is something that is pretty much new that would constrain this type of models. And yeah, so far we really consider this charge current mediated decays, but then the question is, what about neutral currents? Because they are also there. And the neutral currents could also be induced at higher loops if you couple the ALP to leptons. Either left-handed or right-handed leptons, you get these loops that are inducing this, for example, ALP coupling to a strange and the down quarks, and therefore this K to pi decay, K to pi A decays. And then you can write down the similar, diagrams for other decays like B to Ka. And we can compute this SDA induced couplings, and you can find the answer here. And then once that you have this effective couplings, then you can compute these rates. So the charge mode will be proportional to the absolute value of this coupling, the other one to imaginary part because of CP violation. And so you have all the ingredients to compute also these decays and then compare to data. And then again, it's interesting because only some of these searches have been performed. So there is this NA62 that looked for K to pi and some invisible particle. And then there was also this experiment at BNL looking for K to pi E plus E minus, where this is a resonance. And but then there are other decays like K long to pi and E plus E minus, or B to K E plus E minus, that there are no targeted searches. So it will be interesting to see what one could do there. And then for this, we use some measurements that were done in some kinematical region that is similar to the kinematical region for our signal. Okay. And then again, to give you a sense, so these are the plots that we were looking at before, and this is what happened if we add this neutral current decays. And we see that intermediate regions can be probed by this. And overall, there is a lot of complementarity between charge current mediated processes and neutral currents. Okay. All right, so this leads to my conclusions. So in this seminar, I wanted to give you an overview of new activities to test axion-like particles. There are new phenomenological aspects and also a lot of new measurements that could be done in the future. And yeah, that's it.
Thank you for the seminar. Any more questions?
How far is the big dump of this short container based on? So you have a big dump, so the you absorb the rapid, right?
Yeah.
So this is like maybe under
Roughly, maybe a bit less, but that order, yeah.
Number of ions and
Correct.
that
That is true. True.
There is also a unique absorber.
Mm-hmm. Oh, I see. Okay. Mm-hmm. Yeah. Yeah. True. Yeah.
Directly focus we talk is the beam absorber production. It's much closer to your detector. Is in the study we have with the argument. The production of the beam dump location versus the absorber location, they almost contribute equal amount of signal.
Oh, wow. Okay. Mm-hmm. Yeah.
It's a different time. I will use something. Initially points. But hear what you were saying.
Mm.
Yeah, I'm done with something. Ah, you are not yet. Oh, okay, with Rima. With Rima. Yeah, we have other things.
Okay, there are no more questions for Stefania. Let's thank her again. It's
Maybe I just disconnect.
just connect.
Yeah, just disconnect.
Good to see you, Arkady.
Oh,
Yes,
okay.
I'm
Nice to
trying
see you,
to say thanks. Yeah,
Thank-
I'm so.
Nice to
Yeah.
see you, okay.
Oh, okay. Now I can see you too.
Yeah, good to see you. Haven't seen you in a while. Although, yeah, I heard you last week.
So you just okay? No, it's just to show that I'm still alive.
Yeah, I also wanted to come around here just to see you can see I'm also alive, and you can. It's not just a recording of my voice.
Okay, no, good talks. Thank you, Stefania.
Thank you for joining. Okay.
See you, Arkady.
Bye.
Bye.